Good morning. Good morning, everybody. So the title of my presentation is Influence of Printing Orientation on the Crack Path in 3D printed tensile and shear specimens. I should acknowledge the contribution of my PhD student, Liviu Popa, and my colleague, Galatanu. We are all from University Polytechnica Timișoara from Romania. So just before to start, I would like to say that I joined this cycle of conferences, Crack Path, in 2012 in Gaeta, then Ferrara, Verona, and Rome, which was actually online. So I think this was a great initiative of Professor Andrea Carpentieri to organize this cycle of conferences. And I would also want to thank to the organizer of this Crack Path in Rimini. So the summary of my presentation, I will start with a short introduction related to the additive manufacturing of polymeric materials. Then I will present the material that we use and the methods that we use for testing. Then some tensile and shear test results. And finally, I will draw some conclusions. The objective of this work was to evaluate the crack path for tensile and shear test on PET specimens obtained via fused deposition modeling, and also to look on the influence of the raster angle and the influence of the contour. So many of you probably are familiar. The additive manufacturing is an important component of Industry 4.0, the digitalization of the industry. If we are talking about polymeric materials, so we have different techniques which differ on how is the initial state of the material. For example, for material jetting or photopolymerization, material initially is liquid, or material extrusion or sheet lamination, the material is in the solid form, or for the powder bed fusion methods, the material is in the powder shape. So we use material extrusion. This method has some advantages: a shorter production time, it's easy to be customized, reduce the labor cost, is cheaper, relatively cheaper. Also, the printers are relatively cheaper, and the material is cheaper. And with this method, we can reduce considerably the material waste. Where it's used now, it is used in many industries. In automotive, medical, electronics is most used this method, but start to be used on other industries like aerospace, in education, in architecture. So we, as a material, we use polyethylene tetraphthalate glycol, which is a thermoplastic copolymer, which good strength, durability, and flexibility. Mostly used in many industrial applications, has also good impact resistance and ability to withstand high temperatures. As an application, so plastic bottles are probably the most used application, but there are also used in food industry, medical and pharmaceutical applications, can be in the shape of the sheets. So we use a Prusa printer. We use the plate temperature of 60 degrees, the temperature of the nozzle 220 degrees. We use an average speed of 45 millimeters per second. The layer thickness was 0.15 millimeters, and we consider 100% in-field density. We consider three types of in-field. So 0 degree, so this is aligned with the loading direction in tensile, 90 degree, which is perpendicular with the loading direction in tension, and plus minus 45 degrees. So we use three rasters for the in-field. We use classic dog bone specimens for the tensile test, 10 millimeter width and 4 millimeter thickness. And we adopted, actually, there are no standard specimens of standards for determining the shear properties of polymeric materials. So we adopted the ASTM standard, which is for thin aluminum sheets, and we use the same geometry of the specimen. So the tests were carried on our 3 Proline machine in Timișoara. Both tests were done at room temperature and with a loading speed of 5 millimeters per minute. What I would like to say here, we use 6 specimens for each type of test, with and without contours for the tensile, and with and without contour for the shear test. So these are some fractured specimens with the infill orientation at 0, 45, and 90 degrees. What we can observe, we have here a fracture at 45 degrees for 0 and 45 degrees, and we have a fracture perpendicular to the loading direction for the infill, which has the orientation at 90 degrees. We also, for some tests, we also use digital image correlation in order to identify the shear at fracture, and we compare with some specimens that for which we use extensometer, and we found that around 3–4% was the shear at the fracture. Some typical low displacement curves for the specimens with contours. So the maximum load and strength was obtained for specimens aligned at 0 with infill at 0 degrees, then 90 degrees and 45 degrees. At 45 degrees in both cases, so with and without contour, we have a higher energy, fractured energy. So we have a quite big portion of plastic deformation when the raster is at plus minus 45 degrees. If we look on the tensile strength, so for 0 degree, we get the maximum for both cases, with and without contour, which is around 55 megapascals. On this case, the contour has the same orientation with the rest of the infill, so there is no influence of the. We cannot see any influence of the presence of the contour. While for the other orientations, we have this, so we have a degrees of around, let's say, 10% for plus minus 45. So we get lower values for the specimens where we don't have contour. So moving to the shear fractures, these are with contour. What we can see here, so the fracture occurs in this small ligament, which has around 5 millimeters. But with the contour, there are some layers of contour that still remain, so keep the specimen, the two fractured parts together. So at 45 degrees, it's almost the same. While for the 90 degree, so we get some fractures perpendicular to the loading direction, similar with what we get in the tensile test. So you can see here more. So this is a zoom of the fractured area. So we have these ligaments that keep the two parts together for the 0 degrees, and also here for the 45 degrees. And we have this fracture that goes perpendicular to the loading direction. We also use for some specimens digital image correlation in order to see, and the fracture starts also around 3–4% of the tangential shear strain. So for the specimens without contour, so we have here a perfect graph. So we don't have the contour to keep together the two parts. So this is at 0 degree, this is at 90 degree. Also, the crack propagates perpendicular to the loading direction. Some specimens are broken also here in the small ligament. So if we look now on the typical load displacement results. So again, for the 0 degrees orientation, we have the maximum load here. And if we look on the tensile strength, shear strength value, we have here for all specimens without contour, the value is around 10% lower comparing with the values with the contour. Also, having the contour, the results are more close. So here, without contour, we have more scatter in our results. What we were trying to look, so in order to be able to predict the fracture of any raster orientation, so we try to apply the tensile criterion, which is a phenomenological material failure criterion, widely used for anisotropic composite materials. We have used this for some composite materials reinforced with polymeric matrix reinforced with short glass fibers. So what we did, having this result, so we consider the tensile strength at 0 degrees, the tensile strength at 90 degrees, and the shear strength on 45 degrees. So with these results, so we try to predict the tensile strength at 45 degrees. So these are the values coming from the scientific criteria around 44.2 megapascals. And our experimental results, the values that we measured, were 47.8 megapascals. So it's an error of 7.4. What we want to do to print with different infill orientations, 15, 30 degrees, in order to check if it's this criteria could be applied to predict the mechanical properties for different orientations. So I think these are the conclusions. So the influence of the contour appeared for all the specimens on shear test, and for the specimens on tensile test only for orientation at 45 degrees and 90 degrees. So what I can say from this result is that if we want to be sure that we have, let's say, stronger construction, additive manufacturing component, it's better to use such contours around the specimen. If we want to characterize the mechanical properties, so maybe it's better to don't have these contours. So we obtain different crack paths for different raster orientations. We use digital image correlations to identify the strains for tensile and shear test, and we prove that the tensile criterion could be applied to determine the mechanical properties for different raster orientations. Finally, I would like to acknowledge a European project, a twin project, which was coordinated by me. It was ended last year, and it was in durability and integrity of additive manufacturing components. We have other 4 partners here: University of Parma, Trondheim, University of Belgrade, and Institute of Physics of Materials from Czech Academy of Science. So thank you very much for your attention.